this should be on momentarily. Okay, so we are live on YouTube. I'll also do this. Okay, so hello everyone. Welcome to the week 5, and we have this week 2 mini courses. Exceptionally, we have Steve Evans about to start, and Vita Nestoridi in 2 hours. And the small comment, so there was a typo on the website which had the third talk on Wednesday. It is on Thursday, as we've been doing in previous weeks. So without further ado, let's get started. So we are happy to have with us Steve Evans, who will talk today, tomorrow, and on Thursday about tree value chains and their bridges. So Steve,
Great.
is yours.
Great. Thanks very much, Omer. It's wonderful to have this opportunity, and thanks to all the organizers for just organizing this wonderful summer school in these difficult times. Okay, so I'll begin by talking about something that'll lead into the idea of bridges and won't involve trees to begin with one of the very basic things that we probably expose our students to early on in a stochastic processes course. And that's the classical polyurn. So suppose that we've got the classical polyurn that starts with an urn that has a green ball and a red ball in it. It's seeded with that at time 0. And what we keep track of is the number of green balls and red balls that are added to the urn at successive times. And so you all know the mechanism here, that at each subsequent point in time, we pick a ball uniformly at random from the urn and replace it along with one ball of the same color. So here is a realization of a possible first step of the dynamics of the urn, where we picked the green ball and replaced it with another green ball. Okay. And one of the surprising things about the polyurn is that there's some hidden exchangeability going on here. That it's a calculation that you have to do. It's not something that's immediately obvious. That if, say, you condition on at time n+1 there being little g green balls and little r red balls having been added, then the order in which the little g green balls and the little r red balls have appeared is uniformly distributed over the possible strings of little g greens and little r reds. And so in particular, if we look at one step backwards in time of this chain, from time n+1 back to time n, then the backward transition dynamics are given by those two expressions there. Okay, so we go backwards in time like that. Okay, and so now suppose instead of the polyurn, we look at an even simpler stochastic process, namely just independent coin tossing, where we're tossing a coin that comes up heads with probability P, and we keep track of the number of heads and the number of tails. Then, of course, we all know that if at time n+1 we condition on there being little h heads and little t tails, then of course the order in which the little h heads appear and the little t tails appear is of course again uniform over the various possibilities. And the backward transition probabilities for this chain have exactly the same form. Okay, so the take-home message for these two examples, polyurn and coin tossing, is that polyurn run backwards in time has the same transition dynamics as coin tossing run backwards in time. Okay, so I want you to keep that example in mind, and now we'll just leave probability behind for a little while and just start talking about some formalism with trees. And the sort of trees that we're going to be talking about for most of the time are trees that are rooted. They're binary, so each vertex has 0, 1, or 2 children. So of course the vertices that have 0 children are the leaves. And they're ordered trees. So that means we distinguish between a left child and a right child, even when there's only one child. And so such a tree we can identify as a subtree of the so-called complete rooted binary tree, which I'll describe on the next slide. And I want to introduce that with some machinery that maybe looks a little heavy-handed at the moment, but it introducing this sort of coordinatization for binary trees makes things simpler in what follows. So we'll use some notation that's sort of common in the combinatorial literature. This notation 0, 1 star is the set of all finite words drawn from the alphabet 0, 1 with the empty word allowed. So it's the the empty word, the word 0, the word 1, the word 0, 0, the word 0, 1, and so on. And to simplify things, rather than write words as ordered tuples, we'll just write them as lists like that. And then we can think of 0, 1 to star as an infinite directed graph by putting a directed edge between two words if basically we'll put a directed edge between 0 and 0, 0, or between 0 and 0, 1, or between 0, 0 and 0, 0, 1. I mean, just if one word extends the other by a single letter. So it's just the obvious notion of V being a child of U, being a direct descendant of U. And so this infinite directed graph is what we'll call the complete rooted binary tree, with the root being at the empty word. So these dots here are meant to indicate that this just goes on forever here. So I hope this picture's clear here. Okay, so it's just this infinite binary tree here. And then the set of infinite words in the letters 0, 1, which of course aren't in the complete rooted binary tree, we can sort of imagine those as being the kind of like the leaves of the complete rooted binary tree. And we can define a partial order on the complete binary tree by declaring that U is less than V if we can find a directed path from U to V. So in this picture here, 0 is less than 0, 0, 0. For example, so it's just saying, we can find a downward directed path from the first word to the second word. So it's just in genealogical terminology that V's a descendant of U, and this partial order extends in an obvious way to 0, 1 star union 0, 1 infinity. I'm just using the square cup here to emphasize that this is a disjoint union. Okay, so now what do we mean by a finite rooted binary tree? So a finite rooted binary tree is just a non-empty subset of the complete rooted binary tree, with the property that if we have a vertex of T and U is such that U connects to V by a directed edge, then U belongs to T as well. Okay, so if 0, 0 is in T, then because U 0 connects to 0, 0 by a directed edge, 0 has to be in T as well. So of course the vertex, the empty word, belongs to any such tree T, and we think of that as being the root of T. Okay, this is all sounding very pedantic at the moment, I know, but it's just useful to have this terminology, this kind of, as I said, coordinatization of binary trees as a way of thinking about them kind of nice and precisely. Now, what's one thing that we can do with binary trees, and one thing that computer scientists use them for, is for storing ordered lists. And this use of binary trees is called binary search or binary search trees. And so suppose we've got an ordered list of the numbers 1 up to 9 like this. Then we can store that in a binary tree by the following mechanism. We take the smallest number and put it at the root of the tree like this. Then all the numbers that appear in the list to the right of the smallest number, they're going to appear in the subtree to the right. So 3, 5, 2, and 6, they're going to appear in this right subtree. 8, 7, 9, and 4 appear in this left subtree. Okay, then we look at the numbers that are going to appear in the left subtree, and we pick out the smallest one, which is 4, and we put it at the root of the left subtree. And similarly, we look at the numbers that are going to appear in the right subtree, 3, 5, 2, and 6. We pick out the smallest one, which is 2, and we put it at the root of the right subtree, and then we just recurse. Okay, and we just continue going on like that. We look at 2 here. There's numbers to the left and the right of 2. 3 and 5 appear to the right of 2, so they'll go in the subtree below 2 that's to the left of 2. 6 is to the right of 2, so it appears in the subtree below 2 to the right of 2. Okay, so you can imagine writing a recursive algorithm that will describe how this we can associate ordered lists of the numbers 1 up to n with binary trees with n vertices, where when we go down any path in the tree, we see numbers in increasing order. Okay, and so this suggests a mechanism for actually building a random finite rooted binary tree. So we could build a random finite rooted binary tree by taking a bunch of uniform, independent, identically distributed random variables. And, suppose that we had 9 of them, U1 up to U9, and our particular realization of U1 up to U9 had them appearing in this order here. Then we get an ordered listing of the numbers 1 up to 9, and then we could just build the binary search tree associated with that ordered listing of 1 up to 9, and we get a random finite rooted binary tree. So that would produce a realization of a finite rooted binary tree. Okay, so that would work for any value of n. And of course, we could do this now for a whole infinite sequence of uniform inputs and proceed to get a family of growing finite rooted binary trees. So we could do this construction for successive values of n. And what'll be of interest to us is to just keep track of the resulting rooted binary trees. And what we'll do is throw away the labeling of the vertices by the numbers 1 up to n. Then with a little bit of argument, what you can check is that the resulting stochastic process is actually Markovian in its own right. It's pretty obvious that the guy where you keep the labels is Markovian, but if you throw away the labels, that guy is still Markovian, and we'll call that the binary search process. And the rather interesting thing is that the binary search process has very simple transition dynamics. And let's call that guy Tn, and it'll evolve as follows. So obviously T1 is just the trivial tree, the tree that consists of a root and nothing else. And if Tn's a tree with n leaves, then there's going to be n+1 words that we can sort of think of as being neighbors to vertices of Tn that are possible ways of extending Tn to build Tn+1. Okay, so the tree here in bold is Tn, and then here the dotted edges leading to the red circles are all the possible vertices that we could extend Tn to build Tn+1. And it's an exercise to show that the dynamics of Tn are the simplest possible ones imaginable, namely that you just pick from one of those neighboring empty vertices uniformly at random. So that's the way that the binary search tree grows. And I see that I've misspelled probabilities up there. Okay, and so there's a connection with the polyurn here, namely, I'll sort of say it in words for the using the picture here, and then go to the notation on the slide next. Think about how many guys are in the left subtree below the root, and how many are in the right subtree below the root. Well, when we grow at the next step, you see that the number that's in the right subtree is going to the left and right subtrees are going to grow like the numbers of green and red balls in Polya's urn. Okay, because you know, here we've got 1, 2, 3, 4. Okay, and so there's actually you know, 5 possibilities here. So there's sort of like 4 new balls that have been added, and you know, like 5 balls in total to pick from. And similarly, there's 3 new balls to been added, and 4 balls in total to pick from here. And so and that's going to be true for any vertex. So for any word, the sequence of where, if we count the number of vertices in the subtree below V to the left and below V to the right, they evolve like time changes of the numbers of new green and red balls in a classical Polya urn that start with 1 green and 1 red ball. Okay, so this binary search tree process is just like this grand infinite hierarchical system of Polya urns. It's just Polya urns all sort of hooked up together, that we have you know, a Polya urn here and a Polya urn here, and then that Polya urn is decomposed into 2 Polya urns. This Polya urn is decomposed into 2 Polya urns, and so on. Okay. Now there's another Markov chain that arises from a search, a sort strategy in computer science that I won't go through the sort of raison d'etre for it. That'd take me a little too far afield. But that's called digital search. I'll just explain the resulting Markov chain. And again, it takes values in the space of finite binary trees, and it evolves as follows. Again, you start with the trivial tree that just consists of the root. And again, at time n, you've got a tree with n leaves, and there'll be n plus 1 neighboring words that, you know, they're defined in the same way, right? There's these neighboring words that are possible ways of extending the tree. And the way that you extend the tree is to pick such a one with a probability according to its length. And so if the neighboring, a potential neighboring word is a word of length L, you pick it with probability 2 to the minus L. And so we'll use this notation here for the length of a word, sort of absolute value of V, and adjoin it to produce the tree dn plus 1. And it's an exercise to show that if we look at the number of words that are in the left subtree below a vertex and the number that are in the right subtree below a vertex, that those numbers evolve like time changes of the number of heads and tails in fair coin tossing. And so the digital search tree process is then just like an infinite hierarchical system of simple random walks. Okay, so for digital search, the number of vertices in the left subtree is like the number of heads. The number in the right subtree is like the number of tails. And then that decomposes into something that's like the number of heads, something that's like the number of tails, and so on. And so if you put that together with our observation about the connection between polyism and simple random walk, we see that the binary search process run backwards has the same transition dynamics as the digital search tree process run backwards. So two sort of processes with rather different forward dynamics look the same when they're run backwards. And yeah, so rather sort of surprising. So now I'll sort of move on to yet another search scheme, which is called Radix sort. And this is a way of sorting distinct infinite binary words. So, excuse me, so suppose that we've got n distinct infinite binary words. Then a realization that you can make is that you can construct a sequence of n finite binary words, y1 up to yn, such that yi is an initial segment of zi, and y1 up to yn are the distinct leaves of a finite rooted binary tree, and y1 up to yn are the minimal length words with this property. So essentially what you're doing is you're chopping off the tails of z1 up to zn that contain information that you don't need to distinguish the z's from each other. So let's maybe have a picture. Oh, this is hard to read, I realize. So suppose that we've got 3 binary words, infinite binary words. The first one starts with 0, 1, and then has some infinite sequence of letters after that. The next one starts with 0, 0, 0, 0, some infinite sequence of letters after that. The next one starts with 0, 0, 0, 1, some infinite sequence of letters after that. Then we can store those guys in a finite binary tree. Well, we can just associate those with vertices in a finite binary tree just by sort of keeping the finite prefixes of those guys, which distinguish those infinite guys. We just keep enough information, the minimal information, minimal prefixes that distinguish those guys from each other. So does everyone get the idea here that we just need to go to the second digit to distinguish this first word from the other two, whereas the second and the third one, we need to go to the fourth digit to distinguish those from each other. And so we can put them in a tree like this. And that's there's a unique way of doing that. And so that resulting finite rooted binary tree we'll call the radix sort tree for the infinite binary words that we started with. And the depth search, first search of this tree visits the leaves in an order that coincides with the lexicographic order of the corresponding infinite binary words. So if I do a depth first search, so I wander around this tree in a depth first way, so I wander around the outside of the tree, then I visit the words. I visit 0, 0, 0, 0 first, 0, 0, 0, 1, and then 0, 1, and that's visiting the corresponding infinite words in their lexicographic order. And so that's a way of using trees to sort the infinite words. Okay, so let's introduce some notation that we'll need. Let's denote by open face S the class of finite rooted binary trees that can actually arise from this algorithm. So think about for a moment what kind of trees can arise this way. Well, a tree can arise this way if and only if it's either the empty word or it has at least two leaves, and for any leaf of S, the sibling leaf is also a vertex of S. So if you've got a leaf of S, the word that we produce by flipping the final bit of S. So if the last letter of S, the last letter of U is a 0, we flip it to a 1, or if the last letter of U is a 1, we flip it to a 0. So the so-called sibling, sibling means brother or sister, then that'll also be a vertex of S. And so we'll write Sn for the elements of S with n leaves. And so in particular, S1 contains only the trivial tree with the single vertex consisting of the root. Okay, so what happens if we have a radix sort tree for a bunch of infinite words, and we take one of the words away? Well, that's obviously going to remove one of the leaves. Okay, and so we're going to need to understand how that transforms the tree. And so that we're going to call that procedure pruning. Okay, so here's a picture of it. So suppose we prune this leaf. So the infinite word that corresponds to that, we're going to remove that and build the resulting binary sort tree. Well, the resulting binary sort tree is going to be this one. Okay, so here's what the pruning operation looks like, and here in notation is what goes on. So there's two cases to consider. The first case is the easy one, which is not the one that's illustrated in that picture I just showed you, is where the leaf that we're going to prune is not a leaf of the tree. Then where the leaf that we're pruning, its sibling is not a leaf of the tree. Then the pruned tree will be just the rooted binary tree with the same leaf set as T, except that the leaf V's being removed. Okay, on the other hand, suppose that the sibling leaf is also a leaf of T. Okay, so the guy that we're going to prune is a leaf, and its brother or sister is also a leaf. And so then there's a path leading to these guys, right? There's a path of descent leading down to these guys. And what we're going to do is basically sort of chop out that path of descent. So in this case, the pruned tree will be the tree with the same leaf set as T, except the leafed V and its sibling leaf are both being removed and replaced by the single leaf that's at the start of that path leading down to the pair V and its sibling. And this pruning operation, you can check, does exactly what I said, that if T is the radix sort tree for the infinite binary input Z1 up to Zn plus 1, and Yn plus 1 is the leaf of T corresponding the input Zn plus 1, then the pruning operation for the tree T with respect to the leaf Yn plus 1 is the radix sort tree for just the first n inputs, z1 up to zn. Okay, now we're going to build a stochastic process. So suppose that we've got an infinite sequence of IID 0, 1 to the infinity valued random variables with common distribution that some diffuse probability measure on mu. So that means in particular that these guys are distinct with probability 1. And let's set new Rn to be the radix sort tree for these guys. Okay, so this will be the finite rooted binary tree that sort of records the prefixes of these guys that distinguishes them. Okay, and it's a good exercise to convince yourself that this process is actually Markov. And probably the easiest way, at least for me, to see that this is so, is to show that the backwards in time process is Markov, obviously. The forwards in time process is Markov if and only if the backwards in time process is Markov. And the backwards in time transition probability is this is actually not expressed properly. It's it should be this probability is 1 over n plus 1 times the number of leaves v such that S equals kappa TV. That's how it should be said. Okay, so this is not expressed correctly, right? Because there could be several leaves V such that S is the pruning of T with respect to V. This bullet point here is correct though. That the backwards in time guy is obtained by picking leaves uniformly at random and pruning them. Okay, and of course this is what you'd expect from the symmetry inherent in this, that yeah, because of the IID nature of the inputs, the leaf that's going to be picked is just going to be uniformly picked from the various leaves. Okay, and notice something interesting here, that the backwards transition probabilities are the same no matter what the distribution of the inputs are. Okay, so we're seeing that theme appear again, that we're getting processes with different forwards in time transition probabilities that have the same backwards in time transition probabilities. Okay, so now we've said what are the backwards in time transition probabilities. What are the forwards in time transition probabilities? And this again is a good exercise. You know, lots of good exercises here for an undergraduate stochastic processes course. That the Radix sort process is Markov, and the way that it evolves is as follows. If you've got a rooted binary tree with leaf set ls, then there's two cases to consider. One is where what you want to do is you've got y is not a vertex of S, and this guy here, its sibling is a non-leaf vertex of S. And then you want to transition to the finite rooted tree whose leaves are the leaves of S with Y adjoined. Then it's pretty obvious what's got to happen is that the input Zn plus 1 has to be an infinite word that has prefix y, okay? And so it has to fall in this set here. So we let tall y be the set of infinite words that start with the finite word y. And so the probability of this happening is the new measure. Remember, nu is the probability distribution of the successive infinite words z1, z2, and so on. You've got to be picking Zn plus 1 from this set here. The other case is more complicated, and you need to sort of sit down and draw some pictures to sort of see where this is coming from. And that's where you have you've got a leaf y that's in S, and then what you're going to do is add on a little piece of tree that's a path leading from y that bifurcates at the end to two sibling leaves, y prime and y double prime. And so T is going to be the finite rooted binary tree with leaf set that looks like this, right? So you're going to grow from the leaf y, that's going to grow into a path that splits right at the end into two leaves. Then you can convince yourself with a little bit of calculation that the probability of doing that is given by this expression here. Okay, so this actually may be a good place to stop. What we're going to, we haven't sort of got into the full meat of things yet. We've just been introducing various models, and that's going to continue for the first bit of the next lecture. We're going to introduce Radie's algorithm, which generates uniformly distributed finite rooted full binary trees. They're binary trees where every vertex has 0 or 2 children. So they're the sort of things that are counted by the famous Catalan numbers. And we're going to show the connection between that and a process called the Patricia process, which is intimately related to the Radix short sort process. The Radix sort process is kind of inefficient. The way of making it more efficient is an algorithm that's called Patricia, and when you turn that into a Markov chain, you get the Patricia sort process. And then what we're going to do is essentially look at a kind of test case and say, we're going to see that all the ways of running the Radix sort process backwards are just other Radix sort processes. So running Radix sort processes backwards just keeps us in the world of Radix sort processes with other generating distributions. But that's, things are much more complicated if we look at Radie's algorithm or Patricia processes. I know this is just perhaps words for you at the moment. You don't know what these things are, but that's going to lead us into the world of real trees and metric measure spaces. And there we'll see this connection with real trees and the Aldous Hoover-Kallenberg theory of exchangeable arrays and that sort of thing. Okay, so that's what we'll start on in the next lecture. So we'll have one more class of examples of processes, and then we'll start developing some theory about classifying all the possible ways that one can run certain of these tree valued processes backwards. And then eventually I'm going to say something about how this is connected to Martin boundaries and classifying the minimal harmonic functions for these processes. Okay, thank you.
Okay, so thank you, Steve. So let us unmute and thank Steve for this first lecture. And I will stop the recording and we can have questions.